Hello. Today we're starting a very important topic of eigenvalues and eigenvectors. And we're going to use these to solve systems of first order ODEs, but that will wait for a while. So for two mini lectures, I'm going to be talking about eigenvalues and eigenvectors. All right, let's start right off. So first, we need a square matrix. So let A be a square matrix, and its size is n by n. And then we have a vector V that's a column vector, which is the same size as A. So V is an n by 1 column vector. So A times V can be multiplied and gets another vector of size n by 1. We say that V is an eigenvector of A with corresponding eigenvalue lambda, and lambda is a scalar, provided AV equals lambda V. And that's an interesting equation. I'm going to box it. It's a super important equation here. It's the equation that relates eigenvalues and eigenvectors. And remember, this is a square matrix. That's a vector. That's a scalar, and that's a vector. But as a result, both sides of this equation are n by 1 column vectors. Okay. So we're not going to talk today about how you find the eigenvalues and eigenvectors, but we're just going to use this definition. So here's the first example. Suppose I tell you that V1, which is 1 minus 1, is an eigenvector, and it has eigenvalue lambda 1, we're going to figure out, and V2, which is 3, 1, is another eigenvector. So I'm given two eigenvectors of this square matrix, 5, 9, 3, negative 1. Okay, we want to determine the corresponding eigenvalues, lambda 1 and lambda 2. Just going to use that equation. And you notice that this 1 and that 2 are just labels. This is the first eigenvector, V1. That's the second eigenvector, V2. We're not talking about components. All right. So let's just do it. AV1 is 5, 9, 3, negative 1, 1, negative 1. So I'm going to do my thing where you have to use your fingers to multiply, and I'm going to get 5 minus 9, 3 plus 1. So I don't want to do too much in my head. This gives me negative 4 and 4. So they told me that this was an eigenvector, V1. So they're saying that the result is some scalar times V1. So that scalar has got to be negative 4, isn't it? Therefore, lambda 1 is negative 4. That's the first eigenvector. So the first eigenvalue. That's the eigenvalue corresponding to the eigenvector 1 minus 1. Second, we have that AV2 is 5, 9, 3, negative 1, 3, 1. So again, I'm going to do 5 times 3 in my head, 15, plus 9, and then I get 9 minus 1. That's 24 on top, and 8 on the bottom. Okay? And that is indeed a multiple of 3, 1. That scalar is 8. Okay? Therefore, lambda 2 is 8. Okay, so there's a few problems like that where they tell you what the eigenvectors are, and you've got to find the eigenvalues. Okay? All right, so let me do another example, and I'm going to just erase a lot of this just to remind ourselves that AV is lambda V. And something we often do for this is we label them. So we say A times vector labeled with I is lambda I V I. Okay, no, don't want to erase that. So another thing that we do in this set is we talk a little bit about how multiplication of a matrix times a vector is a linear operator. Okay, so let's see, where am I? Suppose a matrix A has eigenvalue, eigenvector pairs. Let's say lambda 1 is 2, V1 is 3, 7, and lambda 2 is 5, V2 is 1 minus 3. And I want you to compute A times V1 plus V2 and A times 3V1 minus V2. Okay, now what's the weird thing about this? I didn't tell you what A is, right? I didn't tell you what A is. Okay? But we're using the linearity of matrix multiplication. Okay. And that is that if I take A times the sum of these vectors, that's A times V1 plus A times V2. Matrix multiplication of A times the sum of two vectors is the sum of A times the first vector plus A times the second vector. Oh, but look at that, we got that here. We know what A times V1 is. This is lambda 1 V1. We know what A times V2 is. This is lambda 2 V2. Right? Because they told us that we have this eigenvalue, eigenvector pair. So that means that this is 2 times 3, 7, plus 5 times 1, negative 3. So this thing here is 10, 14. That's twice 3, 7, plus 5, negative 15. So I get 15, comma, negative 15 and negative 1 as the two components of A V1 plus V2. 15, negative 1. Okay. Now, let's do something similar with A times 3V1 minus V2. Is going to be 3 times AV1 minus AV2. Again, using the linearity. A times a linear combination of two vectors is a linear combination of A times those vectors. Okay, so what is AV1 is lambda 1 V1 minus lambda 2 V2. Okay, so this is 3 times 2, 6 V1 plus, oops, sorry, minus 5 V2. And you can do this more quickly if you want to. Okay, but all right. So to get 6 V1, let's put the V1 and V2 in. This is 6 times 3, 7 minus 5 times 1, negative 3. Okay. So this is 18. 6 times 7 is 42, minus 5 and minus 15. All right. So this is equal to 13, 42 plus 15 is 57. Okay. I figured that out without knowing what A is. And this maybe comes as no surprise. In your linear algebra class, I don't think we'll be doing it. You'll figure out ways to actually figure out what A is. If you know the eigenvalues and eigenvectors of a matrix, you can figure out what the matrix is, because that has all of the information about the matrix. All right. Well, next time, I'm going to talk about the important topic of how to figure out what the eigenvalues and eigenvectors of a given matrix are. Right? So far we've just used the fact that that somebody tells us that we have an eigenvalue eigenvector pair and another one for this matrix and figure out what happens. All right. Well, goodbye.